what I saw on the Taco Bell sign. Unit 10. Wow, who would have thought? Sequences and series, right there at Taco Bell. To be honest, the name of this unit should be sequences and series. Series is the most important part of this unit and what you're going to need next year in BC Calculus. Sequences lays the foundation. Sequences, though, is just a list. I want you to think list, and series, I want you to think sum. All right, so we are going to start laying some foundation with some sequence work and then very quickly jump into sequences with the next video. All right, so what we're going to do today is focus on, of all the sequences in all the world, we're going to focus on arithmetic and geometric, two very famous sequences, and how to write those sequences explicitly and recursively. And then we're going to talk about a little bit about limits as we get ready for series. Limits going back to first semester. Recursive rules you've done before, right? When I want you to think step by step is what you think for recursive. And explicit, I want you to think jump. Geometric, I want you to think multiply. And arithmetic, I want you to think add. Okay, so just giving you those keywords to start with as we start some definitions. Right? As I said, a sequence is a list of numbers. It is ordered, and it is a progression. And the progression, we are talking about discrete values starting either for as low as 0, maybe starting at 1, maybe starting at 4 or whatever, but we don't deal with negative numbers. We are going from 0 or, again, something higher than 0 and going either to a stopping place or to infinity. Right? Again, the list can be finite or infinite. So here is a finite list. Notice that my terms are separated by commas. It is a ordered progression of discrete values. There's nothing between 5 and 8. I am going from 5 to 8. Hopefully you can see that to get from 5 to 8, you have to add 3. To get from 8 to 11, you have to add 3. So the way I progress through this sequence is adding 3. Here is an infinite list separated by commas, still a progression. The dots include and mean the pattern continues. Here is the pattern or the rule. And then it goes on forever and ever and ever. Here's one in, right, the abstract. So instead of saying that my first term was 2 or my first term was 5, I call it a sub 1. The second term was 4 in the second sequence and 8 in the first. I don't like this notation, but nobody cares if I like it. The brackets, again, usually indicate discrete, right? Nothing between the first term and the next term, as opposed to the interval or, the parentheses or the hard brackets. I don't see this a lot. I don't see this one a lot. I don't see this a lot, but I just wanted to try to show you all notation. And if I asked you to expand or list out, you would follow this rule. You would say, well, starting with 1, because equal to 1, I would plug in 1, add 1 and divide by 1, comma. Then I would increase 1 not to a half, not to a third, not to 0.9, but to 2 integers. And I would say 2 plus 1 over 2, comma, 3 plus 1 over 3, comma, yada, yada, yada. So a recursive definition, when you're defining a sequence, is a rule for how to generate the next term from the previous term. So for example, I give you a place to start. The first term is 3. How do you get the next term? The next term is the previous term plus 5, and use n greater than 1 because I've already used 1, told you the answer is 3, or that the corresponding value is 3. An explicit definition tells you how to jump any term. So remember I said that recursive, I want you to think step by step. That's because each time to get the next term, you have to use the previous one. Next term comes from the previous one. An explicit definition allows you to jump to any term. So remember I told you I wanted you to think jump. So any term is your k squared plus 2. So maybe I start this one at 0. K is equal to 0, so your first term would be 2. K is equal to 1. A sum 1 would be equal to 3. You could also write this out as domain and range, right? My domain is 0, 1, 2, 3. And my range is 2, 3, 2 squared plus 2, 3 squared plus 2, so on and so forth. Right? Input, output. Arithmetic sequence. What was the word I told you to think of with arithmetic? Arithmetic, right? Add. Each term is obtained by adding something that sounds kind of funny, but common difference, and we call that common difference D, to the previous term. The recursive rule for an arithmetic sequence is after somebody gives you a place to start, right? So here's use of it. Right? How do you get the term? The next term is the previous term plus a common difference. Right? So this, I used use, I'm trying to throw all kinds of, right? So I told you to start at u sub 1 is 3, right? From the previous slide. You get the next term by the previous term plus 5. Use n's greater than 1 because I already gave you 1. But the explicit rule is I get any term is, I still need the first one, plus that common difference times n minus 1. Wait, that looks familiar. For our example up here, look, any term is equal to the first 3 plus the common difference 5 multiplied times n minus 1. What does that look like? Hello, slope. It's been a long time. Right? That's the equation of a line. It's just that we're dealing with discrete values. So when I talk about graphing n's versus a sub n's, when n is equal to 1, a sub 1 was equal to 3, or u sub 1, whatever. When n was equal to 2, 8. When n was equal to 3, right? Any term, hello, slope. So let's find the first 4 terms. Well, we did that in the previous slide, didn't we? Our domain started at 1, 2, 3, 4. And since we started at 3 and then we had to add 5, 3 plus 5 is 8. 8 plus 5, 13. 13 plus 5, 18. Dot, dot, dot. Graph those, 1, 2, 3, 4. There's my dots in a linear pattern. Hello, with a slope of what? Yep, 5. Because the change in the y value, the range values, compared to the change in the x values was 5 over 1. What? Now, so we found the first 4 terms. What about the 8th term? I could keep going with my list, couldn't I? I just could keep adding 5 and 5 and 5. Right? 18 plus 5. Oh. Plus 5. Plus 5. Plus 5. There's the 8th term. But I could use the explicit one instead of writing all of that out. The 8th term is 3 plus my slope, my common difference, times n. Oh my gosh, 35, there's 38. Woot! Can you imagine the pattern if your d was negative? What would happen? Right, what would happen if your common difference was negative? In other words, as n increased, your range values went down. Let's say your u sub 1 was still 3, but you subtracted 5 each time, right? Go to negative 2. So, as n goes to infinity, what does the sequence go to? The limit of the sequence with a positive d goes to infinity. The limit as the sequence goes to infinity with a negative d goes to negative infinity. Whoa. So let's do some practice. They asked for the common difference, the 10th term, the recursive rule, and the explicit rule. I'm going to do this last. I don't know about you. Right? Because to do the 10th term, I think I'll use the explicit rule. So let's find the common difference. Negative 1 minus 7. No. Negative 1 minus negative 7. Right? 5 minus negative 1. 11 minus 5. 6 is my common difference. So check, I found the common difference. The explicit rule, start with who? Who was our first term? Negative 7. And then to get to the next term, you use the previous term plus 6. The explicit rule is the first term plus the common difference times n minus 1. Let's clean that up a little bit. There's my explicit rule. It is a linear function with a slope of 6 and a y-intercept of negative 13. but I'm only going to start this, right? When n is 1, I'm at -7, and then to -1, and then to 5, then to 11. The limit as n goes to infinity of this sequence is infinity. I'm going to skip down to the third one. Well, let me just say that here, I'm not going to go all the way through this one. I'll let you do that. But notice that what is true about your common difference. 15 minus 26, 4 minus 15, -7 minus 4. Your common difference is -11. So the limit of this sequence is going to go to -infinity. Oh, my Lanta, look, logs. Find the common difference, so log 6 minus log 2. I took AAF and I paid attention. See the log twice with subtraction in between, write the log once, and divide the arguments. Log 18 minus log 6. See the log twice with subtraction in between, write the log one. Oh, yep. The common difference is log 3. So my first term is log 2. To get to the next term, I use the previous term and add log 3. So you might say to yourself, how is it that log 2, is it true that log 2 plus log 3 is that log 6? Yep, because you see the log word twice with addition in between. You write the log word once and multiply the arguments. How about the explicit rule? The explicit rule is the first term plus the common difference times n minus 1. Let's clean this one up. N log 3, I don't want to write the n last because then it looks like log 3n, plus log 2 minus log 3 oh my Lanta. This is an arithmetic sequence with a common difference that is positive. What's its limit? What is the limit of these terms? Positive infinity, right? Limits of the terms where, if you keep going forever and ever and ever. Geometric. In calculus, geometric sequences are the nicest, especially as we turn them into series. A geometric series, remember I told you about multiplying. Remember with an arithmetic, which I told you to think of adding, you added a common difference. For geometrics, you're multiplying a common ratio. And remember, ratio is a fraction, and fraction is dividing. The recursive rule for any geometric sequence is to get the next term, you take your common ratio times the previous term. You start with n is greater than 1 because someone has to tell you what a sub 1 is equal to. So here's my example. The first term is 4. The recursive rule is multiply every previous term by 2. So what's a sub 2? I'm going to do it over here. A sub 2 is 2 times the previous term. A sub 3 is 2 times the previous term. A sub 4 is 2 times the previous term. Again, you can think domain. right? I started with 1, 2, 3, 4, and I can keep going. And my range is, I was given with the first term, I was 4, then I used the 4 to get 8, then 16, then 32. The explicit rule is any term, so this is next term, is the common ratio times the previous term. For the explicit rule, it is any term is the first term. So the thing with explicit, you do need to know the first term, right? The first term times your common ratio raised to the n minus 1, right? So for our example, where our first term was 4 and our common ratio was 2, check it out. Does that work for a sub 1? Yep. How about a sub 2? 2 to the 2 minus 1 is 2 to the first. 2 to the first is 2 times 4 is 8. Check. What if I want to find the 8th term? I find the first 4 terms, done. I could keep going to find the 8th, but I could use my explicit rule and say a to the 8th is 4, the first term, times the common ratio to the n minus 1, right? 2 to the 7th, what is that? 128. So really, that's 2 squared. That's really 2 to the 9th, right? Check my math on that. Now, let's think about this graphically. N, a sub n. When a was 1, I was at 4. When n was 1, 4. When n is equal to 2, I was at 8. When n was equal to 3, I was at 16. Hey, what pattern is this? Exponential, baby. Swoosh! Swoosh! I hope you're not surprised. Right? Exponential. Swoosh. What is the limit of an exponential function where your base is greater than 1? Infinity. So let's do the same thing with these geometric. Find the common ratio, not the common difference. 10th term, thanks, but I'll do that last. The recursive rule and the explicit rule. So what am I going to do here? I'm not going to take right when I was looking for the common difference, I did 6 minus 3. Now, can you see that this is not arithmetic? What if I didn't know that this was geometric? I would do 6 minus 3, which would be 3. 12 minus 6 is 6, not arithmetic because the difference was not common. I'm going to look for a common ratio. So I do 6 divided by 3. 12 divided by 6. 24 divided by 12. And hopefully you can see that common ratio is 2. And of course you can see multiply 3 times 2 is 6, 6 times 2 is 12, 12 times 2, right? That wasn't that hard. I really didn't need to do that. But that's what it means to be geometric, that you have a common ratio. So what's the recursive rule? Right? The recursive rule says what's the first? The first term is 3. How you get the next term is common ratio 2 times the previous term. Right? Doesn't that make sense? 2 times 3 is 6. 2 times 6 is 12. But what's the recursive rule? The recursive rule says use the first term and your common ratio to generate any of the other ones. So I think I'll use that for a sub 10. Two to the ninth. 5, 12 times 3. 6. 1, 5. Check my math on this. 1, 5, 3, 6. Okay. How about the next one? I'm not going to go all the way through the next one again, just to make sure you're doing, right? 1 divided by negative 1/2. Negative 2 divided by 1. 4 divided by negative 2. Your common ratio is negative 2. What about this one? Again, these numbers are fairly simple, so without going through this process, hopefully you'll be able to see that R is equal to 1/2. Right, so you can do all of these, but I want to talk about the graphs again and this idea of a limit. So geometric, right, is exponential. Exponential, right? A times my base to the x. It's just that I'm dealing with discrete, so it's not going to be a connected swoosh. So when your base was greater than 1, my common ratio was greater than 1, swoosh! That limit was infinity. I should have done that in blue. How about when my base is negative 2? Look at these terms. What happens? My first term is negative 1/2. My second term is 1. My third term is negative 2. My fourth term is 4. My fifth term, right? What the heck? Remember how we talked about exponential functions can't have a base that is negative. That's illegal because it's not a swoosh or a slide phenomenon. It's a bounce phenomenon. We're not in exponential functions, though. This is a sequence. In our sequence, we are allowed to have a common ratio that is negative. But what is that limit? Can you describe that limit? Does it go to infinity? Well, part of it does. Does it go to negative infinity? Part of it does. Well, this limit does not exist, right? There's no one description of the end behavior. But what about the purple one? The purple one has a positive base, but with a ratio, right, a positive common ratio, which if you're thinking about exponents, right, is your base. It is between 0 and 1, starts off at 48, comes down, comes down, comes down. You cutting in half. That's your slide. What is that limit? The limit of those terms is 0. Kind of cool. This, in calculus, not only do geometric series make you happy, but ones that have limits that go to 0 make you pretty happy. So this idea of a limit of an infinite sequence, the limit of an, right, and this is the notation I told you I don't really like. The limit of is said to converge if the limit as the terms go to infinity is equal to a number. Finite L just means number. If the limit of the terms is infinite, in other words, you get positive or negative infinity, or does not exist, the limit of the sequence diverges. So all of those graphs, so I think of those graphs, right? Diverging, we had the arithmetic sequence. Remember, the arithmetic sequence went like this or this. Geometric sequence went like this or went like this. Oh, you know what? This is terrible drawings. Ah. We had our arithmetic with a positive d as n went to infinity. These terms went to infinity. With a negative d as n went to infinity, the terms went to negative infinity. Diverging. For a geometric sequence, as n went to infinity, we had the swoosh. Diverge. For n that was negative 2, we had the bounce scenario. D and E. The limit of the sequence diverges. But the geometric sequence where the common ratio was a half, the n behavior was asymptotic, right? The horizontal asymptote at 0. The limit of those terms was 0. 0 is a finite number. That sequence converged. It collapsed to the horizontal asymptote. Neither arithmetic approached an asymptote. The swoosh exponential did not approach an asymptote, and the bouncy one did not approach any asymptote. Right? All the other ones had limits, but the limits were infinities, right? Positive slope, negative slope, exponential swoosh. So look at this sequence. -1, 1, -1, 1, -1, -1. So this is the rule. -1 for, think about graphing that. What does that graph look like? Right? So does this sequence converge or diverge? Is the same thing as saying what's the limit as n approaches infinity. So if you're confused, graph it. -1, 1, -1, 1, -1, right? As n goes to infinity. N is 1, n is 2, n is 3, n is 4. But you have 1, -1, 1, -1. What is that behavior as n goes to infinity? Does not exist. What does that mean? Converge or diverge? How about that one? 2 plus 2, 4 plus 2. This is arithmetic. Arithmetic with a positive or negative d is still a linear pattern that goes to either positive or negative infinity. We call that divergent. How about this one? 48, 24, 12, 6, 3, 3 halves, 3 fourths, 3 eighths, 3, right? Asymptotic. Approaches this horizontal asymptote, the limit of the terms as n goes to infinity. The limit is 0. 0 is a number. Therefore, we say this limit, this sequence converges. How about that one? What's the common ratio? Right? Can you see this pattern? Well, there's not a common ratio. This isn't geometric, but they gave me the rule, right? So it's not arithmetic and it's not geometric. It's just a different type of series, but I can still think about the graph. What is this graph doing? The first term is 1. The second term is a half. The third term is a third. Can you see that this graph is also reaching a horizontal asymptote? And if you think of that graph in Algebra 1, Algebra 2, and Pre-Cal, you know what that continuous graph looks like. So now just think of it, right, as dots as n approaches infinity. This list of terms approaches 0 as well. Therefore, we say this sequence converges, collapses to a horizontal asymptote. How about that one? Can you see what's happening there? Right, again, it's not arithmetic, but can you see, they didn't give me the rule, but can you write a rule for this? What's the rule that you would maybe put in between here? If this is n on the bottom, 1, 2, 3, and 4, this is n, what's the top? Yeah, n plus 1. Can you think about that graph? Think about that. What if I said what if I gave you this function? Whoops. And I said, what's the n behavior? You would say, oh, Ms. Getz, you taught us that when the powers of the numerator and denominator are equal, the n's are pulled off to a ratio of the leading coefficient, so there is a horizontal asymptote at 1. I then taught you at the beginning of this year that is another way of saying what is the limit. And I'm just going to put the n's back. What is that limit? That limit is 1. That number, right? That is your limit. That limit is a number, but that number actually came from, it is a limit of terms of this sequence. The limit went to a number, not an infinity and not a DNE. So what do you say about this sequence? This sequence converges. OMG. Now, this idea of converging and diverging, convergent, divergent, pretty good book series, not so great a movie series, is super important in BC calculus and then beyond, but it's not really the convergence of a sequence that's important. It's of a series. But this first idea of a thinking of converging and diverging, that's new language, and tying it to, right, your previous and prerequisite knowledge of graphs, right, and what their end behavior looks like, and tying the idea of convergence to a limit and graphically to a horizontal asymptote as n goes to infinity. Okay? Pretty cool. All right. I will see you in our next video.